This afternoon we begin with Damien Calaque from the Université de Montpellier, and he's going to talk about the operatic approach to Drinfeld associator and more.
Okay, thank you very much. It's really great to be here. So I will be talking about an operatic view on associators. And I will start with an introduction that will essentially not mention operads, just to give some motivation and like history about the what these associators are about. So the original motivation it comes from deformation theory and more specifically deformation quantization. So let me give the setup. So we start with G, some Lie K algebra. And all along this series of talks, K will be a field of characteristic 0. We consider T some Casimir element. So it's an element in the second symmetric power of G, which is G invariant. And let me start with let me call this problem 1. The question is to find a braided monoidal deformation, which is formal, meaning that the deformation is over the field of power series in one variable, let's call it H for some reason, of the category of representations of the Lie algebra G. So that is a symmetric monoidal category, and we want to deform it as a braided monoidal category. And we want to deform it such that like two things are satisfied. So first of all, so the braiding will be given by like the usual switch of two representations on which you may act by some element of the second tensor power of UG. So that there's you're going to have an element R, which is almost the braiding, which will start with 1 tensor 1 plus H times like T over 2 plus higher order terms in H. And that's an element that lives in UG square double bracket H. So it acts on any pairs, on any tensor power of two representations. And basically the braiding is just switching to representation and acting by R. And we also want the associator phi, which gives the associativity constraint to be the usual thing, which switch parenthesis, and to be deformed by an element which writes 1 tensor 1 plus higher order terms in H bar. And it lives in UG to the power of 3 because it acts on 3 representations, on the tensor product of 3 representations, double bracket H. Actually, these things have to be invariant, but let's, it's built in whenever you want a braid monoidal deformation. Okay. So Drinfeld who actually was the one who was interested in this problem, observed that you can require a bit more. You can impose that R has the following form. It's exponential of HT over 2. And then look for a phi that can be expressed by universal formula involving T and the Lie brackets of G. All right. So let me give you some ideas about what kind of universal calculus you get in this context. So the universal calculus is the following. So we have T, which lives in the second symmetric power of G, which is G invariant. So let's view it as an element in G tensor G, G invariant. So a symmetric tensor is in particular a tensor. And let's even view it inside the second tensor power of the universal enveloping algebra, still G invariant. So we view G inside this, and all our tensor calculus will live inside this place here, where you have several copies of the universal enveloping algebra, and everything is G invariant. Let me introduce some notation. So typically, I'm gonna write T12 for T tensor 1, which is something that lives in UG tensor 3, still G invariant. Similarly, I'm going to write T23 for 1 tensor T, living in the same space. And from there, you can infer the kind of like notation that I will have. Tij, whenever I and j are indices running from 1 to n, Tij is T acting on the ith and the jth tensor component of UG to the n. All right. Now, this satisfies some relations. And these relations are the following. So basically, G invariance of T imposes the following relation that T12 commutes with T13 plus T32. Let me also mention that, well, T12 is just the same as T21, just because T is symmetric. And there is an additional relation in case you have 4 indices which are disjoint. So if you have 4 indices, I, J, K, L, then Tij and Tkl, they commute just because they act on completely disjoint tensor components. So all these relations, like, more generally, this relation that I wrote for like 1, 2, 3, it holds whenever you have a triple of 3 disjoint indices. You have the very same relation, like Tij commuting with Tik plus Tkj. And so for every n, these relations define you a Lie algebra. So so it's generated by these Tij, which are equal to Tji, for I and j going from 1 to n, and plus these relations. That defines a Lie algebra, which is called the Konod-Rindfeld Lie algebra. All right. So now let me rephrase the problem 1 in more universal terms. So like which I will call problem 2. The idea is to find, phi. So, yes? Sure. Oh, so we are taking the free Lie algebra generated by this symbol Tij, and we mod out by the ideal generated by these two relations, like Tij commutes with Tik plus Tkj, and Tij commutes with Tkl. Is that fine? Oh, so that indeed, that's a, well, a priori you don't need to specify, like, I didn't say that it was a graded Lie algebra, but indeed it is a graded Lie algebra, and you can put the generators in degree 1. No. It's a graded Lie algebra, like but without signs. Sorry. So like, but I didn't want to say graded at this point. So it's just a Lie algebra. Yes. It has a grading, but it's not like it has nothing to do with homological algebra. It's just a like there's a notion of a graded Lie algebra. It's just a Lie algebra like with a weights indexed by integers. But yeah. No, I will. No, I will not talk about this. Yes, yes, it is true. Yeah. All right. Other questions? It is the holonomy algebra of the configuration space of points, of n points in the plane. It's true. Yes? Right. Why should you care about problem 1? So problem 1 is related to deformation quantization. So that there's this, so this element T, so it's a first order deformation of rep G as a braided monodal structure, as a braided monodal category. And there's this whole question in deformation quantization. Whenever you have a first order deformation, can you extend it as a full formal deformation? It's an integrability problem. There are in principle abstractions for this. And typically, if you take a single Lie algebra and you try with a T and you try to do this and you compute the abstraction, there are abstractions. And the whole idea of Greenfeld was to transport this to a universal question, like, and there, I'm not saying the abstraction do vanish, but you can prove that there exists a deformation which is like purely universal. I don't know if this answers your question. Another way to rephrase it in terms of of operads, like rep G together with the data of T, that's a shifted Poisson algebra in the category of linear categories, and the braided monodal category, that's an E2 algebra in linear categories. So we're trying to deform something which is P2 in E2. But I won't talk about this in these lectures. Other questions? All right, so problem 2 is now find some phi, which is going to be a formal power series in 2 variables, x and y. And yes? I don't quite understand the question. I don't. Where does the, like, this first relation come from? Is that the question?
You can speak with me,
No, it doesn't come from there. Like this relation, that's just the G invariance of the tensor T. I think this is really something that you can like do as an exercise. Prove that G invariance implies this relation. But it does not, I mean, it has nothing to do with the braided monodal axioms. what I'm about to write now has to do with the braided monadal axioms. Okay, so we want to find a phi, which is a series in like a formal quadratic series in two variables. And you should really think that x is going to be t12 and y is going to be t23. Satisfying a bunch of relations. So first of all, well, you want phi to be invertible, so you want phi to be group-like. Which means that phi, you can write it as exponential of a Lie series in x and y. And actually, this is equivalent to ask that delta of phi is phi tensor phi, where delta is the unique co-multiplication that sends x to x tensor 1 plus 1 tensor x and y to y tensor 1 plus 1 tensor y. The second condition is, well, you want a phi yx to be phi inverse. So whenever we switch the two variables, we get the inverse of the series. But that's not the most important thing. So the most important relation is the following one. So we want that, and I'll explain the notation. So there's this equation, which is the pentagon equation. So you want phi 1, 2, 3, phi 1, 2, 3, 4, phi 2, 3, 4. I'll explain this notation like in less than 5 minutes. So there's this pentagon equation, and it's an equation that lives in, let's say, the completed universal Olympic algebra of T4. And finally, there's the hexagon equation, which is phi 1, 2, 3, exponential T23 over 2, phi 2, 3, 1, exponential T 3, 1 over 2, phi 1, 2, 3, no, 3, 1, 2, sorry, exponential T 1, 2 over 2. And this must be equal to exponential of the sum of the three terms, like T12 plus T13 plus T23, all these over 2. All right, so let me explain these relations. So first of all, if you know about braided monadal categories, these two equations should, I mean, sorry, this last one lives in the universal Olympic algebra of T3. So they really look like the axioms for braided monadal categories. That's just 1 minute. So that's the pentagon axiom for the associativity constraints. And that's the hexagon that gives you that you get re-representation of the braid group. Yes, there's a question.
You write them one next to the other, you're using the composition of the series, right? So
no, product of series.
Oh, product.
Yes. Yeah, product of series. All right, so let me explain the notation now. Delta is the unique coproduct that sends generators to Lie algebra-like elements. So they send the x to x tensor 1 plus 1 tensor x and y to y tensor 1 plus 1 tensor y. It's the Sheffield coproduct, yes. Okay. So this superscript there, which I wrote here, they are called insertion coproduct maps. So first of all, whenever I write phi, I either view it as a series in two variables or as something that lives in the universal enveloping algebra of T3. So it's just that you can view phi as phi of T12, T23, and that you see it is in the universal enveloping algebra of T3. And usually I would write this as being like phi 1, 2, 3. Okay. So now, what are the kind of maps that I have? So whenever I write something, let's say 2, 3, 4. So blank 2, 3, 4. That's a map that goes from T3 to T4, and that essentially shift all the indices of the T's. So it sends Tij to Ti plus 1, j plus 1. Okay. So I'm not going to define fully the insertion product maps. I'm just going to give you examples of how they work so that you get an idea. Later on, they will get some operatic interpretation, which will be like way more clear. So the one with the hat is that we have series. So it's just a completion of the universal enveloping algebra. The Tij's have degree 1, and you complete with respect to this grading. Is that fine? All right. The most important thing to notice is this thing. So like if you have 1, 2, 3, 4, that defines a map from T3 to T4. And it does the following thing. So typically, T12 is going to be sent to, well, the 2 is on the second place, and here you have two numbers, so you just split them in two parts. So what you get is T12 plus T13. So you keep the 1, and 2 becomes like 2 plus 3 here. So just sum over all indices that appear at the second place. Like typically, if you have T13, it's sent to T14. And for the last one, T23, well, the 3 is the third place, it becomes a 4. And the 2 here, it's become a sum of 2 and 3. So you get T24 plus T34. Okay, so that's how it works. And of course, like you can put permutation in the game. So typically, like when you have phi 2, 3, 1, you take the expression with the Tij, and you apply the permutation that sends 1 to 2, 2 to 3, and 3 to 1. All right. So that's the problem 2, and any solution of problem 2 gives a solution to problem 1. And it does so for every pair G and T. All right. So there's a nice feature about the phrasing of problem 2 is that so the sets of solutions of problem 2, which is like spoiler, it is what people call the set of associators by definition. And here, let me give you a little warning. Later today or maybe tomorrow, there's a slight subtlety about this definition, but I will say something about it when I. there more audio now? Does it work again?
Yeah.
Okay, my fault. Sorry. There's this cable. Okay, it may happen again. Sorry, what was the question? Oh, that's a case, or I'm sorry. That's just the ground field. Like everything depends on the choice of the ground field. That's a K. It has nothing to do with the H, the H bar of before. Okay. So yeah. So what I want to say is to give two remarks now. So the first one is that, like if you're a bit used to it, this insertion coproduct maps looks very much like partial composition for operats. So and more precisely, we will see that the collection of Tn, they form an operad in a bit of a weird way in the category of Lie algebras with symmetric monadal product, the sum. So this is why it looks like an operatic structure, but in a bit of an uncommon way, and we will see how it works later. So that's the first thing. And the second thing is that a very good, like a source of torsors is given by the following feature. If you have any category, C, let's say, and you have two objects, and you look at the sets of isomorphisms from one to the other. This is a torsor where the automorphism of the first object act on one side, the automorphism of the second object act on the other side, and I mean, it basically, it really acts free and transitively. The only question you have to sort out is if this thing in the middle is empty or not. Once it's not empty, you know that its size is exactly the size of these two groups, and these two groups are isomorphic non-canonically to each other, right? So a large source of bitorsors is given by bitorsors of isomorphism between two objects. And so the main goal is to reinterpret like the set of associators as some iso between two things, and where the two things are some sort of operads. All right. And before, okay, so before telling you what will be the next step and the actual starting point of these lectures, let me mention that there's a very important theorem of Drinfeld's, which tells you that associators do exist. So there's a first of all, so the things go the following way. So Drinfeld first proved that they do exist for over C, over the field of complex numbers, by using transcendental methods like integrating some differential equation. And then from this, you can deduce, using that you have a torsor, that they also do exist over the rationals. And there's a bit of an argument to prove this, but we won't prove any of these two statements in these lectures. All right. Yes. Oh, I mean, there can be, of course, there are solutions for specifically algebra which do not come from the universal solution. Yes. But what does it mean universal somehow? With a, oh, sorry, with a different choice of R, you mean? Yeah, yeah, I don't know. I would suspect that the answer is no, but I'm not quite sure. We just want one solution. Well, it's also satisfactory to describe the set of all solutions which are universal, which is this torsor of associators. But if you're interested in a specific case, like for a specifically algebra, yeah, you don't know what the size of this of the set of associators for a specifically algebra would be. So like the advantage of the operatic approach, well, first of all, it's kind of satisfying to have a marginal perspective on something which is defined purely by equations, but it's very well suited for various generalization. Or variations on associators. So there's a lot of variants of associators which have been introduced. And every time like people like, I mean, it's kind of painful to figure out what's the exact equation you want to satisfy to have a good theory. Well, if you go through the operatic approach, like the theory tells you exactly what equation you should find. And like the equation are rather some property, like you have an abstract definition of something, and then you prove that this definition is equivalent to satisfy a bunch of equations, which come from like having something presented by generators and relations. So yeah, so so like in these lectures, we will see the case of Drinfeld associators today and probably tomorrow as well. Cyclotomic associators and elliptic associators. And okay, let me give a table of like all kind of things occurring in this associated theory, and where these lectures, I mean, what we'll talk about exactly. Just to give you the landscape. All right, so actually there's a like all this business. You can run part of this machinery for like you choose an oriented surface, sigma, and a finite group gamma acting on it. So you can fix the genus, fix the group, and then you can ask several questions like, what is the correct notion of associators for this in this framework? You can ask yourself, is there an operatic definition? Then there's the question of proof of their existence. So let me give like in genus 0, there are essentially two situations. Either the group is trivial, or more generally, you can look at some group Z over NZ, a cyclic group acting by just a rotation in the plane. So like the first line is it's just the Drinfeld associators. The second line is the cyclotomic associators. Cyclotomic, which were defined by Enriquez. So the operatic definition here, yes. Yes. Yeah. Okay. But is there a question to repeat right now? Okay, cool. No worry. I will try to do this. Okay, so the operatic definition of Drinfeld associator, you can find them in the book of Benoit Fraisse. And there's a pre-operatic approach which is due to Barnaton. And actually, if you read Drinfeld's paper and you know about operades, you see them, really. And the existence proof is due to Drinfeld. For cyclotomic associators, the operatic definition is due to Martin Gonzalez and myself. And the proof of existence is due to Benjamin Enriquez. Then you can go to genus 1, or no, genus 0. There's this weird story in genus 0. You can find you can take any finite subgroup of PSU2. Then, like, people don't exactly know what associators are, so even less about what's the operatic definition. Even though there's like, in the existence proof, there's a very important ingredient, which is the Kniznik-Zamolodchikov equation, which I don't want to talk about, but it's a weird situation where we do have the ingredient for proving things, but we don't know what we're looking for. Right, so then you can go to genus 1. In genus 1, and if you take a trivial group, these are the so-called elliptic associators, which were also defined by Enriquez. The operatic definition is also due to Martin Gonzalez and myself. And the existence proof you can find in like the KZ equation was introduced by myself, Benjamin Enriquez, and Pavel Ettinghoff. So there's also a story which is a mix of line 2 and line 4, which is called ellipsotomic associators. I don't want to talk about this. It's just a bit technical. And I want to point out that in higher genus, even with a trivial group, like the definition of associators, I don't think there's a commonly accepted definition right now, but there's Martin Gonzalez as a proposal. And for an operatic approach, you can find it in one of his papers, but also I think there's some work of Ricardo Campos, Najib Idrissi and Thomas Ulvarer. And for the existence proof, there is some work on the KZ equation by Benjamin Enriquez in higher genus. Yes? Yeah, so what is the symmetric model category to deform? So that's the point. I think like when you go to this generalization, it becomes less clear the approach like via deforming categories. So for the second line, it is still something that you can phrase in terms of braided monoid category over a braided monoidal category. So we will see that when you go to this cyclotomic case, there is there will be braid groups in the game, and like it will be a case where one of the strands of the braid group will be distinguished, and that's like typically a module thing. For the elliptic case, already it's a bit difficult. So Enriquez and Ettinghoff, they introduced the notion of an elliptic structure on some pairs of functors. Like I don't know, it's interesting, but it's kind of like I think, overcomplicating things. And I think like if you see the operatic approach, like things become completely clear. So after that, you can claim that the correct modular structure to deform, like you have an operad, you just look for algebras of this operad in a category, and then you can check that these things are exactly the elliptic structures that Enriquez and Ettinghoff introduced. They are operads in groupoids, so they have a diagonal. They are operad in spaces if you want. So yeah. Okay. All right. So I can start with the genus 0 case. So the main goal for the first part now is to give the operatic approach to Greenfeld associators. So basically, if you remember what is here, so the main goal is to define A and B and show that the set of isomorphisms in an appropriate category is the set of associators. So that's what we're going to do right now. Oh, I brought the super expensive Japanese truck. Sorry. All right, so let me start with I need some, it's a bit boring, but I need some conventions on operads and groupoids. So let me fix first some symmetric modular category. And I need a bunch of assumptions. So like I wanted to have small colimits. I just want to be able to talk about coinvariance in this category because like when you define operads, at some point you have to take coinvariance. Yeah, so I want them to have small colimits and I want the tensor product to commute with them. And just to like reassure you, the only examples I will use are C being sets together with a Cartesian modular structure, C being groupoids with, again, the Cartesian modular structures, maybe some variations on groupoids, like pro-unipotent version. I will talk about this later. And the other, like the most unusual thing is I'm going to look at Lie algebras with modular structure being given by the direct sum. All right. Okay, like that's a bit unusual as a convention, but let me write units. So for the operads, yeah, so yeah, it commits with what I need. Yeah, I agree. Sorry for that. Basically, like it commutes with taking coinvariance, so that's going to be fine. Thank you. Right, so there's this one operads in sets that I like in the category C that I want to consider. It's like I want to call units, and in ID So it's just the unit in arity 0 and 1, and it's like the initial object otherwise. And the convention that I will take is that all operads will be like all what you want. So they will receive a map from units, and this map will be an isomorphism in arity 0 and 1. So they will be reduced if you want. So whenever I say operad, so all operads, and by operad I mean like a unital monoid in this category of symmetric sequences for the circle product, will come with a map from this operad unit such that this map is an isomorphism for n lower or equal to 1. So they will be reduced if you want. Okay, and I just want to point out that unit is different from the operad, which is like the unit for the circle products, which is 1 in arity 1 and nothing elsewhere. So that's why I'm really writing units. Sorry for that. Sorry? So the reason for having this is that we will need to encode deleting operations, where typically when you have operads defined like over braids, you want to be able to remove one of the strands, which means that you need like a specific and canonical zero-array operation that's when you compose with it, it deletes something. That's the only reason why I need this thing. All right. I need some bit of convention and notation again, or all right, so there's this weird notion of what we call fake pullback. I don't have a better name for that. So assume that we have like two operads like O and P, and these are operads in the category of groupoids. And assume that we are having a morphism of operad between their operad of objects, which are operads in sets. Okay, so whenever you have an operad in groupoids, you can forget the arrows. Just remember about the objects of these groupoids. You get an operad in sets, and assume that we have a morphism of operad in sets between these object operads. You can define the fake pullback of P along this F. So it's an operad in groupoid. All right, so the objects of the fake pullback, so the operad of object of the fake pullback, it's the operad of object of O, of the source of this morphism. Okay, and now if I'm looking at the morphism, so the arrows in the fake pullback in array n from some A to some B, that's just the arrows in P between the image of F of A and the image of B. That's a bit of a weird thing, and that is not a categorical pullback. That's why I'm calling it a fake pullback. And typically, I want to give you an example. And in order to give you this example, I need to specify a few things. So the operand I'm going to consider is the following. So there's a first operand that I want to like call COB. That's an operand in groupoids. Objects are just sequences. I don't know. They're just permutations. Or if you prefer, like, I don't know. Indexing. So like in array4, that's an example of an object. Okay. So I'm writing permutations just as sequences of numbers where they are all distinct and between 1 and n. And morphisms are braid's which are compatible with this. So instead of giving a formal definition, let me give you an example of a morphism. That's a morphism in RED3. Okay. And obviously, the group weight structure is like composing by stacking things vertically. And the operatic structure, it's really a substitution rule. So that's a typical operatic thing. So the partial composition is like what you're gonna have. Let me try to write an example. I'm sure it's not gonna work, but anyway. Yeah, with the partial composition, I always write it in the incorrect order. Yeah. So like, let's do a simple thing. So like, probably it's wrong, but I mean that I'm inserting this here. Basically, you thicken a bit this strand here, and you replace it by this here. So that gives you, like, this one remains the same, and then you replace this thing by a small here. So that's 2, 3, 1, 3, 2. Okay, so that's how you write the composition product, the partial composition product. Okay. Yes, thank you. All right, so that's the operand of braid, if you want. It's an operand in groupoids. But I said that I would give you an example of a fake pullback. So now I want to consider PA. It's the operand of parenthesized permutation. So objects or permutations equipped with a maximal parenthesization. So typically, let me give you an example of an object. So that's just as before. And let's say we have this thing. That's an example of an object. It's an operand in sets. So morphisms are just like identity morphisms. So there's no non-identity morphism. And composition is again substitution and renumbering. So I think I don't need to give example of this. And now there's a morphism from the object of this operand PA, which is itself, if you want, and it has a morphism to the operand of permutation, which is just another name for the associative operand. which sends the parenthesized permutation on the underlying permutation. Like typically it sends 3, 2, 4 with parentheses 1, 2, 3, 2, 4, 1 here. Okay. And now, yeah, now we can try to describe the fake pullback. So yeah, let me give a name for this map. Let's say Q. And the fake pullback of, okay, so what I forgot to mention is that the associative operator is the operator of objects of COB, of the operator of braids. And when you compute the fake pullback, it defines what people call the operator of parenthesized braids. So objects of these operators are going to be, well, by definition of the fake pullback, that's just this operator here. So object will be parenthesized permutations. And morphisms, let's look at what could be a morphism between, let's say, 3, 2, 4, like this. Well, that's bad. 2, 1, 3, let's say. 2, I don't know, 1, 2, 3, like this here. We've just said that such a morphism is just a morphism between the image. So I just need to specify a braid. So here it is. Typically, like what I'm allowed to do is this, like this. Okay? So that's an example of a fake pullback that will be important for us. All right. Other questions so far? No. I still need a bunch of like technical notions. So I need to discuss a bit pro-unipotent completions. Yeah, I'm sorry. There's still a bit of categorical stuff. So pro-unipotent completion is as follows. So I want a functor that take a groupoid, like a nice like set, like groupoid in sets, and to give me something that is complete for some, like that I can linearize somehow and complete. So I need an intermediate category, which is, let me call this like cat coage K. So this is the category of small categories enriched over complete filtered co-associative, co-commutative, co-unidal, co-algebras. So my morphisms are co-algebras, which are co-associative, co-unital, co-commutative, and complete filtered. And this category is symmetric monadal. So whenever I have two such things, and I write the tensor product on objects, the tensor product is just the Cartesian product of objects. And on morphisms, whenever, yeah, so I have a morphism, like a space of morphisms in C tensor D from a pair CD to C prime D prime is just defined by the completed tensor product. So that's just hom in C from C to C prime, tensor product completed, with home in D from D to D prime. Okay. And so whenever you have a groupoid, there's a functor that goes from groupoid to these gadgets here, which basically like, so if you, there's a functor from groups to co-associative, co-commutative, co-unitary coalgebras, which takes the group algebra. Okay. Now, if you have a groupoid, so it's kind of a group with several objects where the product of the group becomes a composition. So the group algebra of a group, not only it's a coalgebra, but it's also an algebra because you can multiply things just as you multiply them in the group. Now, if you have a groupoid, what you get is one of these gadgets. It's still, the home spaces are still co-associative coalgebras, or co-commutative, etc. And now, what was before the product for the group, it becomes just a composition categorically. So there's a functor. It's actually a symmetry model functor, which goes from groupoids to this category. Yeah. That's over a specific field. Okay. So what it does is the following. So it sends a groupoid G to GK. So it's kind of its K linearization. So objects of GK is just the objects of G. And yeah, that's where it becomes a bit technical. So the morphisms in GK between two objects. So what you do is you take the morphisms in G between these two objects. You take the vector space generated by this, and you complete it. But then I have to tell you with what I complete. So now I want to explain what filtration. Well, so there's a subcategory. So let me write I for the kernel of the co-unit, because like every such space. So let me write I A B for the kernel of the co-unit from home G A B to K, right? So for every pair of objects AB, you have this I A B, and these things do compose well. So like, I mean, it's really an ideal, even in the categorical sense. So typically, you can take the subcategory of this this K-linear, I mean, this linearized version of the groupoids, and you take the subcategory where you only recall the morphism which lives in these I's, and you can take the K spoiler of this, like namely things which can be written as composition of K times something that lives in one of these I's, and that defines the filtration on your coalgebras. Yes. Sorry. Oh no, it's yeah. So sorry. It's like it's yeah right. Exactly. And the co-unit is the thing that sends any element to 1. Sorry. So you define the co-unit. So epsilon of some G, where G is really in the set, it's 1. And you define the coproduct to send any G to G tensor G, right? So that defines the filtration, and you complete with respect to this filtration. So that's really, I mean, if you know how to compute the group algebra and you complete the group algebra of some group, that's the exact same thing, but with several objects instead of just one. Okay. And the point is that the above functor has a right adjoint. So this functor, yeah, notation is probably bad, but anyway, has a right adjoint. Let me call it G. It goes from this category of categories and enriching coalgebras to groupoids. And essentially, it sends such a category and enriching coalgebras to the following groupoid. So it says, again, it has the same objects. And for the morphisms, you take group-like elements. Okay? And the pro-unipotent completion of a groupoid, it's the composition of these two. Let me recall the notation for this. Yeah. I first apply this kind of k-linearization process and then apply the functor G. That's a lot of G's, sorry. That's a definition. And the point is that this, like all this is send operad to operad because it's compatible with the symmetric model structure. So whenever we apply this pro-unipotent completion functor to something which is an operading groupoid, we get an operading pro-unipotent in k pro-unipotent groupoids. All right. Yeah, how much time do I have? 15 minutes. Okay. No. All right. So, like now, with all we've done so far, we have access to the first player. Like, you know, I needed to define two guys and tell you that associators are the isomorphisms between these two guys. So the first guy is the pro-unipotent completion of this opera of parenthesized brace that we've seen. So that's the first guy we're interested in. And now what I want to do is define the second one. Yes. Yes. So how do you work? Yeah, so like this guy has a universal property, first of all, like the pro-unipotent completion. Anytime you have a groupoid which maps to a pro-unipotent one, a k pro-unipotent one, it factors through the pro-unipotent completion. So that's the first thing. And also it's not so difficult to describe. If you know about Malchev completions, that's essentially the same thing. So if there was no object, just one object, it was a group, it's basically, you do the construct, I mean, the construction is as follows. You take the group algebra, you complete it, and then you take the group-like element. That's not so much of a big deal. If you prefer, you can take primitive elements, that's the Lie algebra, and you exponentiate it, and that gives the exact same thing. So it's not so frightening. Yes. All right. So now I want to talk about chord diagrams, and some people call them infinitesimal braids. And I think the name infinitesimal braids, it's actually good because, you know, if you think about the original problem, which was a deformation quantization problem, there was something which was an infinitesimal deformation and we wanted to integrate it. So what we've just described so far, the PAB, like even completed, that's the side of the story which is already kind of quantized, if you want. So that's the side of the story that we have integrated. And now what we're going to talk about, it's the infinitesimal version of the problem. And the idea is that we want something that relates the two. So so recall the Lie algebra Tn, and let me just, I want to emphasize that it depends on the choice of a field K. So it's generated by these Tij's, which are equal to Tji. So it's a Lie algebra generated by this with relations Tij, Tkl being 0 if, again, I mean, ijkl are like pairwise disjoint, and Tij, Tik plus Tkj, this commutes again if ijk are pairwise distinct. Okay, that was our the Cohn-Rietveld Lie algebra. So the claim is what I said before, is that this algebra, this collection of Lie algebra forms an operator in so sorry, it's a graded Lie algebra, so it's and what I mean by graded, there's no signs, it's just a Lie algebra together with a grading, okay? And the grading is just generators have degree 1. And these relations are homogeneous, so we really get something graded. No, because when you say graded Lie algebra, some people think it's a Lie algebra in the category of graded vector space with the monolith structure given by like the Kosul sign rule. There's no Kosul sign rule here. It's minus all the time. Yeah. Bracket xy is minus bracket yx, wherever the degree of x and y is. Yes. That's the point when I say there's no sign. There's this one sign, but no other sign. Okay, now the claim is that the collection of the Tn's is an operator in the category of like graded Lie algebras. Again, that's just graded in the sense we've just discussed, together with the direct sum. So first of all, it has to be a symmetric sequence. So the symmetric group action is by permuting indices. What I really need to define is the partial composition product. So yeah, to make things easier to write, let me say that another way to describe an operator is, instead of describing it like as a symmetric sequence, you can say that it's something that to every finite set associates, let's say in this case, a graded Lie algebra. And then you have substitution rules that are given by the composition product, and it should be invariant by the action of bijection, which corresponds to the action by conjugation here. You'll see it's just easier to phrase things in this way. So we have like I and j finite sets. And let me take some little s in I. So I want to define an operation circle index S that goes from Ti plus Tj to T, well, union of I and j, but now I remove S, right? That's where I substituted it. Okay? Well, I'd rather write, yeah, I'd rather write this. That would make more sense. All right. So here again, by Ti, I mean the exact same thing as before, except that instead of having I different from j running from 1 to n, I have I different from j inside the sets I. So it's a direct sum. Let me tell you where 0 t alpha beta is sent. Well, it's easy. The index here does not change for j, so it's t alpha beta. You see, if I had to express it using like 1n, I would have to shift my my indexes. That's what happened when in the insertion coproduct maps that we had in the introductory part. And now, if I have Tij here and 0, it is sent to, well, first of all, Tij if S is neither I nor J. It's going to be sum over all P in J, Tpj if S is I. So namely, if S is I run the sum over all P, which are basically substituted with S, which is I. And if S is J, it's the other one. So it's sum over P in J of Tip if S is J, right? So, and this is really a good exercise to check that this thing, it's exactly the insertion coproduct maps I introduced in the beginning. It's just like in different notation, but it's really the same thing. Right, so we define the operative chord diagrams indexed by K to be the completed universal lumping algebra of this T. And here by completed, I mean that T, like Tn for every n is a Lie algebra with a grading. And I'm taking the completion with respect to that grading, right? So I'm allowing to have, when taking the universal lumping algebra, I'm allowing to have infinite sums as soon as the degree increases over the sum. All right, so that's called a horizontal, like strictly speaking, we should call them horizontal chord diagrams. And maybe if you look in the literature, you'll see Tij being represented by a diagram like this. With a little chord between I and J. So you have strands, vertical strands, and you link any two guys whenever you have a Tij. And it's useful to depict the relations now using this these pictures. So typically the relation that Tij commute with TKL, so the first relation over there, it's going to be that, like you can write it that way. So it's IJKL, IJKL. You have Tij, TKL, and then you can just like make the product the other way around. That's the same thing. So somehow, if you have two chords which do not touch the same strands, they commute. You can like move them above and below the other. It's fine. And the second relation, it's sometimes called the four-terms relation. So every time it's IJK, IJK, IJK. And we have Tij and then Tik minus Tik, Tij. That's the term that corresponds, like the difference of these two, that's the commutator between Tij and Tik. And if you add the commutator between Tij and Tjk, So that's going to be like this. You get 0. So that's the equation. Okay, and you can actually check that this this partial composition here, you can reinterpret it pictorially as cabling operation in the very same spirit as we did with braids. So that's that can be useful sometimes. All right, and so now I can define the last player. Well, the second and last player. So, like this is a universal enveloping algebra of something. It's completed with respect to infiltration. Remember that the universal enveloping algebra for Lie algebra, that's a co-associative, co-commutative, co-unital coalgebra. I've completed it, so it lands exactly in the category I was talking about before, except that it has just only one object, right? So this CD K is an operad and its object category, its object operad, sorry, that's just the operad which has like one operation in every array. So we can consider the morphism of operad P that goes from parenthesized permutation to like points. That's just the terminal morphism. And we define parenthesized chord diagrams to be the fake pullback of CD of chord diagrams over this. So let me give you typical examples of arrows or morphisms, if you want, in the groupoids that we have in RET3. That, yeah, so sorry, no, so PACD, that's an element in, that's something in cat coach. We will take its associated groupoid at some point, but at this moment, this is, so what we have, it's an operad in the category of small categories enriched over co-associative coalgebra, etc. At this point, there's not yet a groupoid. Yeah, I'm sorry. Yeah, the morphisms are not in a groupoid, but in this enriched category. Let me give you 3 examples, or yeah. So there's first like H. It's just T12 times this. And that's just like another way to depict this guy. The horizontal chord diagram with 2 strands. And I think H is a good name for that guy. Then there's X, which is just 1 times the permutation. So yeah, I think X is also a good name for this. And finally, you have A, which is like 1. So 1 lives in UT3, and you make it times this. Recall that's just it's just a way of depicting morphisms, because like before, like we were just taking the same morphism as before, except that now we have parenthesized permutation. So we just need to, like, it's just a way to remember that we started from like this parenthesization to the opposite one. So we draw the line that way, but we could as well, just a matter of drawing. We could just draw it vertically. It does not change anything. And the cross here, it just means that we permute them, but there's no over or under crossing here. It's just a permutation. There's no braid. Right, so these are elements, example of morphism there. Sorry? Yeah, that's a good point. N would be a good name. It's just for associator. Yeah, so I'm probably over time now. So let me just go very quickly to the next thing, and I'll explain things tomorrow. So like it's really a definition. Associators are isomorphisms from P, A, B, K hat. So the pluripotent completion of the operad of parenthesized braids to the underlying group weights of the operad of parenthesized permutation. And they're not exactly all isomorphism. There are those isomorphism which are the identity on objects. Because these two operating group weights, they have the exact same operad of objects. So we just want the map to be the identity on objects. So in other words, like the K associators, we write this as iso plus. So this plus means identity on objects in operads in K groupoids from P, A, B, K. I'm just writing a formula for the sentence I wrote before. So that's a short name for K pluripotent groupoids. Yeah, there are groupoids. Yeah. All right, so I'll probably end with this. I just told you in the very beginning that there was a little caveat. So like just as a teaser for next talk. So the main result I want to explain next time. So next time I will introduce growth and educational groups and explain that associators defined in this way are the same thing as associators defined in the way of the like that we did in the introduction. So the theorem we will state tomorrow is that these associators are the same as associators from the introduction. And this is not quite true because associators, so if you look at what happens here in RAD2, in RAD2, like in PAB, you have like one generating element, which is the braiding. And you have to send the braiding to something. And there's something in here that's going to be exponential that will live in exponential of T2. T2 has just one generator, which is this T12, and there's no room for anything else. So your R here, you have a one parameter family of images, like it's going to be exponential of lambda times t, and you have to choose this lambda. And in the definition, in the very beginning of the talk, in the introduction, I've put this lambda to be equal to what? To 1. So like in here, there's this little caveat, like in the intro, you have to replace everywhere exponential t over 2. Every time you see an exponential t over 2, replace it by exponential lambda t over 2, and lambda should be part of the data of what an associator is. So that's the phi and the lambda, such that all this is satisfied. All right, so I'll come back to this tomorrow anyway. And tomorrow we'll talk about the growth and dictational group and the cyclotomic version. Okay, thank you.
Does this work?
Question? Yeah. So what do you mean? So you're asking like, I'm not sure I understand the question. Are you asking like, do you have like concrete description of these two guys or of isomorphisms?
Where is the idea of those guys from? I mean, is there a natural intuition that brings you there somehow, or?
So the natural intuition for the left side here, so this PAB, that's really when you like the way the Reinfeldt phrased things was in terms of braided model categories. And if you want to talk about what are braided model categories, these are algebras over some operad, and this operad is this one. Like if you're more like a topologist, that's a group-weight model for the little disk operad actually, because the little disk operad is made of KP1. So yeah, that's a model for this. Yeah, probably tomorrow I will say a few words about configuration spaces and how you can get this as like fundamental groupoids of configuration space of operad with respect to specific base points. So maybe like the geometric intuition is you have the configuration space of that's going to be a spoiler. So you have the configuration space of points in the plane. There's a way to compactify it using like Fulton method for some compactification. And like this compactification has a structure of an operad via the boundary inclusion. And if you take the strata of the boundary of maximal codimension, you actually get an operad in sets, and that's the operad of parenthesization essentially. Like, and if you take you apply like fundamental groupoid with respect to this sub operad of objects, you get exactly this. So that this part has a very geometric description, and this other part is if you forget about PA, that's really the operad of holonomy algebra of your configuration space as well. Like that's somehow a way to get it. So if you know a bit about the formality of configuration space, what you can prove like using like much more elementary things that what we're doing here is that the configuration space of points in the plane is formal, and as a consequence, in particular, you have that it's the pre-nipotent completion of its fundamental group is isomorphic to the completion of its associated graded, and you have an explicit description of the associated graded as the exponential of the Conrad-Reinfeldt algebra. And somehow, if you want this, having an isomorphism like this, it's having a collection of formality isomorphism for all configuration space, which is compatible with the operatic structure. I don't know if it answers your question, but
So this parameterization thing is
No, it's really like when you have configuration of point in the plane, you can look. The idea is to have specific base points for when you take fundamental groupoid, but base points which are compatible with the operad structure. So the first thing you do is you take points lying. So you choose a line, so the horizontal line. So you restrict yourself to configuration space of point on this line. The compactification will give you the stash F polytopes. And the vertices of this stash F polytoph, which are the codimensional maximal codimension strata, are exactly parenthesization of like linear orders. So that's this operad PA. Yeah. Is there a precise link between the composition in CDK and in the composition for the Prelude operad? I don't know. Oh, Bruno has an answer. Mm-hmm. Yeah. I'm not sure I can repeat this, but I don't know if people got this online or not. No. Oh.
I was just saying that there is an interpretation. So Joan was asking, is there an interpretation of the operatic composition of the Drinfeld-Kono operad? Yes, you can. You take a graph with n vertices and some edges, and you insert them one inside another, and you take the sum of all the edge that come to the guy that you insert in. This is an operad. And then it's an operad which is bigger than this one. So you may ask, what is the smallest sub-operad? Well, you need to take an infinitesimal version of that guy. Okay, and then you ask for yourself, what is the smallest sub-operad of this guy? And this is the one which satisfies the Drinfeld-Kono relation. So in that way, you recover the Drinfeld-Kono relation as a universal operadic property. Thank you.
I don't know. Other questions? Yes, so it is true. Like, okay, so it is true that having an associator, if you rephrase associator as isomorphism between operad and groupoids that way, like there's some work to do to actually show that such a thing, you can deduce the formality of the little disk operad from this, because the formality of the little disk operad is phrased somehow in a Kosul dual way from this. Here you have fundamental groupoid, and you would rather like to have chains on some space. And here you have Lie algebra, and rather you would have like also the homology, let's say. But Tamarkin proved that from this you can get you can deduce the formality of the little disk operad, and like by some other work by Tamarkin, you can go back to the original problem and prove that it also gives a solution to this. So there's a bunch of interrelation between like various problems which are related to the little disk operad. I'm not sure I can draw the exact landscape right now, but it is true that there are deep connections between deformation quantization, like the formality theorem of Kontsevich, Etinghoff-Kasdan quantization of Lie algebras, and the formality of the little disk operad and associators. And there's like a lot of interconnections between these things. Yeah.
So somehow you're saying that this result, having an associator, is some kind of a co-formality statement. Am I right? Because you're phrasing it on the level of Lie algebras and groupoid, etc.
I don't know. I don't know any.
Of course, because this is the course of Alexander tomorrow. That's why I'm asking the question, and maybe I'm asking it for Alexander. So Alexander has a notion of a causal space, which is at the same time formal and co-formal. So the question or exercise for Alexander for tomorrow: are these guys causal spaces? Are they formal, co-formal, and well, okay? So I don't want to spoil too much, but maybe Alexander, can you say something in that direction, or? Alexander, maybe he has the right of not being here.
Yeah, no, it's. I'll say a few things, but let me not go into that right now.
Okay. Okay, thank you very much. Is there any question?
No, so I don't think there's a nice. So there's the question about like the conceptual explanation for this fake pullback. Yep. I don't think there's a nice conceptual definition. It's just that typically you would have an operad, and you would like to like make a bit bigger the set of objects, and you would like to make compatible with it the morphisms, and that's a way to do this. You can view it as a kind of semi-direct product construction. It's not exactly this, but it looks a bit like this. So I don't. Maybe Geoffroy has a better explanation. Je t'amène. I switched from speaker to chairman.
So, yeah, one way you can interpret this in that particular case is that, so what happens here, you make the operad of object becomes free. This operad PA is free on RET2 operation. And that makes this operad PAB a cofibrant replacement of the previous thing in a suitable mole category of operads. So that's, you could say it's an explicit cofibrant replacement in a certain mole category of operads and groupoids. Well, I'm not talking about the construction of fake pullbacks in general. I'm just talking about this one.